Okay, so in this video I will complete the section of exercises on finding the absolute max and absolute min on a closed interval. And we'll review a few items here. The first thing is the extreme value theorem, which I call EVT. It states that a continuous function on a closed interval always has an absolute max and an absolute min. Furthermore, these will occur at either critical numbers or endpoints. And how do we find them? First, we find the critical numbers. That's detailed in previous videos. What that means is we find the derivative, we set it equal to 0, and we solve for x. Bang. Or we find where the derivative does not exist. Second, we're going to evaluate the original function at the critical numbers and the endpoints. Finally, the smallest of those values is the absolute min, and the largest is the absolute max. So there you go, in a nutshell, what it is that we're working with here. So let's go on to problem number 23. In problem 23, we have y is equal to 3x to the 2/3 power minus 2x on the interval from -1 to +1. First thing we're going to do, take the derivative, y prime. We'll use the power rule here, bring down the 2/3, multiply times 3, x to the subtract 1 will give us -1/3, and the derivative of 2x is 2, so minus 2. We'll just simplify that a little bit. 2/3 times 3 is just 2x to the -1/3 minus 2. Ready to set that equal to 0. And we can do this in a number of ways. I'll move the -2 over to the other side. Divide by 2, and that gives me x to the -1/3 is equal to 1. Now x to the -1/3 is really just 1 over the cube root of x, and that will equal 1 only when x is equal to 1. However, a value of x equals 0 will make that derivative undefined. And so I'll put a note up here. At x equals 0, y prime does not exist, and so x equals 0 is very much a critical number as well. Alright, now what do? We evaluate the original function at each of the critical numbers and endpoints, and so we want y of -1. You'll notice that that 1 is both a critical number and an endpoint, and that's fine. We'll still evaluate it only once. Alright, we're going to plug in -1 into the original function. Because that is to the 2/3 power, it has a power of 2 and a root of 3. The power of 2 is going to make -1 become positive, so we have positive 3 minus 2 times -1. So 3 minus -2 is positive 5. Plugging in 0, I simply get 0. Plugging in 1, I'm going to get 3 minus 2, which is 1. And you can see that our absolute max is at x equals -1, y equals 5. The absolute min is at x equals 0, y equals 0. So you can see that that critical number 0 was very important. That's a point where the derivative does not exist. Alright, we're going to go on to the next problem, 25. And we have g of t is equal to t squared over t squared plus 3 on the interval from -1 to +1. In this case, I would use the quotient rule here. To me, it seems like that would make it simpler than doing the product rule along with a chain rule. So we get low, but either way is fine. D high minus high, D low, all over low squared. We'll simplify that up and we get 2t cubed plus 6t minus 2t cubed, and so those 2t cubes will cancel out. T squared plus 3 to the second. Alright, so when those go away, we have 6t over t squared plus 3 to the second power, and we're ready to set that equal to 0. Remember that a rational function is 0 when its numerator is 0. The only value of t that makes the numerator 0 is t equals 0. It's undefined when its denominator is 0. But because we have t squared here, we'll make any value we put in positive or 0 at the least. When we add 3, we'll always have a positive number in the denominator. So there are no values of t that make the denominator 0, and so we have only one critical number, t equals 0. We're going to test the original function at the endpoints and critical numbers. When we plug in -1 into t squared over t squared plus 3, the negative ones are going to become positive. We get 1 over 1 plus 3, which is 1/4. Plugging in 0, we'll get 0 over 3, which is 0. Plugging in +1, we'll get 1 over 4 again. And so we have our absolute min at x equals 0, y equals 0. We have our absolute max, both at -1, 1/4, and +1, 1/4. Alright, for the final problem in this set, we have h of s is equal to 1 over s minus 2, which I will rewrite as s minus 2 to the negative first power. And we're working with the interval from 0 to 1. We find the derivative, and we'll use the power rule with a chain rule. So we bring down the -1, s minus 2 to the negative second, multiply by the derivative of the inside function, which is 1, and that leaves us with -1 over s minus 2 quantity squared. A rational function is 0 when its numerator is 0. And the numerator will be 0? Never, because the numerator is -1. And it's undefined when its denominator is 0. Well, that denominator will be 0 when s is equal to 2, but that's outside of our interval. So we're not really worried about the fact that s could equal 2 and make the derivative undefined there. Actually, even if 2 was in our interval, we wouldn't count it because 2 is not a point on the graph. And I'll make a note of this down here. A critical number must be a point on the original function. It means that x value has to be in the domain of the original function. Must be in domain. If it's not in the domain, like 2 is not in the domain of h of s, then it cannot be a critical number. Alright, so there are no critical numbers, and we only need to test this function at the beginning at the two endpoints. So h of 0, h of 1, plugging in 0, we get negative 1/2. Plugging in 1, we get negative 1. And so our absolute minimum is at negative 1. And our absolute maximum is at negative 1/2. And that does it for this. What I want to do last is to show you how you would use your graphing calculator to verify your results with these types of problems. Okay, now we want to put in the expression for the number 23, and we have 3 times x to the 2. A quick reminder, whenever you're putting in a rational exponent, you have to always place it in parentheses. So we have 3x to the 2/3 minus 2x. And so there's our function. Now, since we're only interested in the interval from negative 1 to 1, I'm going to go over to the window and just set my x min to be negative 1, x max to be positive 1, my x step or scale to be 1. The y values we'll leave as they are, and we'll go in to look at the graph. Now, we're looking for the highest and the lowest points on the graph on that interval. And you can see that they occur at the left-hand endpoint. That's our max. And since the left-hand endpoint is negative 1, we can do second calc value negative 1 and get 5. And that's exactly what we got over here for our absolute max. Our I tells us that the absolute min is at 0. So we can do second calc value 0, and there you go. We have our absolute minimum at x equals 0, y equals 0. So this is a great way to let the calculator double check your results. If you had a mistake in there, you could go back and find it in your algebra, or it's possible that you put your function in wrong, so you also want to double check your function definition on the calculator. Now, the calculator can do all of this for us. However, we're here to learn the calculus behind all of this, so we're only going to use it to double check our results. And that'll be it for this video and for this set of problems.